Good morning, everyone. Today, I would like to tell you about our recent work on understanding the interplay of particle conservation and long-range coherence using quantum computers on the cloud. My name is Emanuele Dalla Torre, and I'm the principal investigator at Bar-Ilan University in Israel. Our group deals with the dynamics of quantum complex systems. We have been lucky to be supported by the Israel Science Foundation as well as commercial partners in the field of quantum computing. For this work, in particular, I would like to acknowledge discussions and collaborations with Matt Rigor, Maxime Dupont, and Bram Evert from Rigetti. Our group deals with the key problem of solving many-body quantum problems. Think of a complex quantum molecule or even a material whose equilibrium or non-equilibrium properties you are interested in computing. As you all know, this problem is exponentially large in the nanoparticles. The traditional way to assess these problems is to make approximations, for instance, using analytical tools or quantum field theories. In recent years, people have also used classical supercomputers to simulate systems of intermediate sizes and have gained a lot of information about those systems, also sometimes combining approximations and classical computations. In the field of quantum simulations that was pioneered by Richard Feynman, we would like to simulate a quantum system using another quantum system with a larger degree of tunability. In particular, this program has been very successful in the field of ultra-cold atoms, where one can simulate the dynamics of electrons using atomic atoms that move in optical lattices and more. Here, I would like to propose that quantum computers on the cloud can also serve this purpose of simulating many-body quantum systems. For the last few years, we have been very active in this field, and we have published several works in which we studied different aspects of many-body quantum systems, including topology, long-range order, quantum state encoding and detection, and more. What is important is that, for me, is that in each of these works, we were able to use a quantum computer on the cloud to perform a proof of concept experiment that demonstrated the effect that we were describing theoretically. Today, I would like to tell you about our recent work in which we simulate a Bose-Einstein condensate. So let's start with the key question of what is a Bose-Einstein condensate. As you all know, there are two possible definitions. One is the macroscopic occupation of the ground state of a ground state. The second definition is about interference, or if you want, the presence of phase coherence between condensates. And this can be seen, for instance, by taking two clouds of ultra-cold atoms and letting, basically in a BEC state, and letting them expand. In this case, this picture will give rise to interference fringes. For instance, here I'm showing you an experiment by a group, and also other groups demonstrated the same effect. The quick question then is, what is the difference between a Bose-Einstein condensate and a laser? Because both definitions apply to Bose-Einstein condensates, but also to lasers, in which, as you know, first of all, there is a macroscopic occupation of a given mode of the cavity, and second, clearly there is a phase coherence that can be probed, for instance, in a two-slit experiment that is analogous to the interference experiment performed here in Bose-Einstein condensate. So we are here focusing on one possible distinction between BC and lasers, which is the presence of particle number conservation. Indeed, in the Bose-Einstein condensate, the particles are atoms whose number is conserved throughout the experiment. So if you take, say, 100,000 atoms in a cloud, that number will not be modified throughout the entire experiment. You cannot create or destroy experiments or destroy atoms. In contrast, in laser, the number of photons is a quantity that all the time evolves. First of all, because atoms are emitted from the cavity. Photons are emitted from the cavity. This is essentially the light that we see of the laser. And also the gain medium creates photons. Why this is important in terms of phase coherence? Because as you all know, number and phase are canonically conjugates. Hence, if the number is a conserved quantity, so if we do not have any fluctuations in n, the uncertainty principle will tell us that there are very large fluctuations in phi, in the phase. So that's indeed what happens in a Bose-Einstein condensate, where the particle number conservation makes the global phase undefined. In contrast, in a laser, the global phase is defined, and indeed it can be measured by simply probing the electric field that goes out from the cavity and that is emitted from the cavity, and the phase of the electric field is just the phase of the laser. So if I told you that in a BEC there is no global phase, how can we understand this interference experiment? And what was understood is that this interference experiment is basically a measurement of the phase. So when you measure the phase, you obtain a specific value. However, if you repeat the experiment, you will obtain many different values. So at each experiment, you will obtain a different phase for your Bose-Einstein condensate. Because the uncertainty principle is an uncertainty, is an inequality, one can also have situations in which both the number and the phase are undefined. And indeed, such a situation can be created in Bose-Einstein condensates of light, in which the photons of the light condense, such as in experiments of dye molecules, and one can have large fluctuations of both the number and the phase. What is common of all these states, the BC, the laser, and the BC of light, is that nevertheless, there still is long-range coherence. This is one defining property of these states. And the long-range coherence is associated with the relative phase between the particles. So while the global phase, if you want the center of mass phase, is undefined, the relative phase between the particles has a long-range order, is well-defined. So how can we simulate those situations in a quantum computer? So first of all, we prepare a coherent state, which is just a superposition of 0 and 1. This is to mimic a situation in which the photons have a well-defined phase, like in a laser state. And in a quantum circuit picture, this can be very easily realized by just applying Hadamard gates on all the qubits. But this state clearly does not have a well-defined number of particles, right? Because its qubit is in a superposition of 0 and 1. So what we do, we measure the total number of particles, but not directly, but through an ancilla. So we do not want to destroy the coherence. If we just measure the qubits themselves, then we will destroy the long-range coherence. What we do instead is to apply an ancilla that will measure the total number of particles. And in general, we will need a logarithmic number of ancillas. Then, if we want, we can post-select the correct number. We can post-select a given number of particles, and this will lead to a state in which the total number is well-defined and which is analogous to a Bose-Einstein condensate. So having prepared this state, we would like to probe it and to make sure that indeed it is a BEC or a laser. How we do that? So we look at the order parameter, which in this case is S theta, defined as the sum of Sx and Sy. If you want, this is just the total spin in the XY plane. I'm going now to show you two-dimensional plots in which the azimuthal angle is the phase, like in the XY plane of the Bloch sphere, and the radial coordinate is the amplitude of the order parameter. In a laser state, as you can see here, the highest probability occurs when the phase is 0. So as I told you, we have prepared the state. This was the initial state, which is just all the qubits in superposition 0 and 1, and then the global phase is 0. In contrast, in a BEC, which is obtained by post-selecting a given number of particles, then the global phase is undefined. There is a 360 degrees symmetry, which leads to 0 expectation value for the operator, because indeed the probability of having positive and negative outcomes is equal. However, in experiments, we can actually probe the entire full distribution, so the entire distribution function of the operator S theta, and not only the expectation value, and observe that the highest probability occurs for large values of S theta. The first state that we considered is a state in which we measure the total number, but we do not post-select. So this is analogous to a BEC of light, where, as you can see, you have a large phase fluctuations. The global phase is undefined because we measured the total number of particles. However, the total number is undefined because we have not post-selected. Now, how do we know that these states have long-range coherence? The way to do it is to observe that the absolute value squared of S theta, the average absolute value squared, is associated with the expectation value of Sx squared plus Sy squared, which can be written as the correlation between all the particles. So the fact that this value is large, so the fact that S theta has a large absolute value is associated with a very large relative phase between the spins. And indeed, in all these situations, we see that the highest probability occurs in the outer ring, either as a point in the laser or as a ring in the BC states. So let me conclude by showing you some experimental results, which we have performed on the Aspen class quantum computers by Righetti. We have used 4 qubits and 1 ancilla. In principle, for 4 qubits, one would need log 4, which is 2 ancillas. However, due to the hardware limitation and to the noise, we obtained better results using only 1 ancilla. In this case, as you can see, the global phase is not fully symmetric, and this is related to the fact that the single ancilla does not allow us to completely measure the number of particles. So we have reduced the number of particles fluctuations, but not to 0 level, and as a consequence, the global phase does not have a global symmetry, does not recover the global symmetry, and this is both in the ideal calculation that does not take into account noise, as well as the real hardware. So why is this interesting? First of all, because this is a way to benchmark current quantum computers, because in this case, we know how to compute the expected values, even analytically. We can compare the experimental outcomes with the theoretical predictions and benchmark the functionality or the noise of the quantum computer. I also think that the quantum computers are really a new theoretical framework that can be used to describe many-body quantum physics and allows us to think about problems that otherwise would have been maybe not thought about. In this case, for instance, we have compared the coherence, as I described before, so as the absolute value of theta, for the BC state and the laser state, and we have found that in the BC state, the coherence is larger than in the laser state. This is because in the laser state, one has all possible particle number, including the 0 particle number, where the coherence is 0, while by post-selecting a given number of total particles, we actually obtain the largest possible global phase. This can be understood in a Bloch sphere analogy by thinking that by reducing the fluctuations in the Z component, we are actually making the state more with more phase coherence in the XY plane. And this is indeed related to the concept of phase stiffness that is achieved in superconductors and superfluids by interactions that squeeze the local number fluctuations and make the phase more stable. Thanks for your attention and have a nice day.